For this section, we're going to be talking about logarithmic functions. So to start off with, we define logarithmic functions by saying given f of x equals b to the x, so given an exponential function of base b, then f inverse, so f with that -1 symbol above it, so f inverse of x is equal to log base b of x. And this is the logarithmic function of base b. Okay, so just to clear up what that's saying, if you're given an exponential function, then the logarithmic function is its inverse. So what must be true if that's the case? Well, if you take log base b and you plug b of x into it, then the result has to equal x. And if you take b and raise it to the power of log base b of x, then the result also has to equal x. Whenever you plug inverses into one another, the result always has to be x in both cases. So this proves these two are inverse functions, no matter what base we're dealing with these logs. And just like with exponential functions, the log base has to be greater than 0 and not equal to 1 and a constant. So from here, we're going to write log base 2 of y equals x in exponential form. We're rewriting the equation that we were given. There are two ways to go about this. I'm going to show both. The first way is what's technically happening. If we want to get rid of the log and change this to an exponential equation, then to do that we need to plug each side of the equation into the inverse function. What is the inverse function? It's the exponential expression of base 2. Because we have a log base 2, the inverse is 2 to some power. So we raise each side of this equation with a base of 2, treating each of the original sides as the exponents. So now this becomes 2 to the log base 2 of y equals 2 to the x. Well, 2 to the log base 2 of y should just equal y, because these are inverse functions. We're left with just what's inside of the log when we plug an inverse into the other. So y is going to be equal to whatever's on the right side of the equation, which is 2 to the x power. Okay, so now that we did the technical way, and if you prefer this way, it's completely okay to always use that, but the shortcut method for this says that whenever you have a logarithmic equation and you want to get rid of the log, you take the base and draw an arrow showing that you are moving it over as the base of the other side of the equation. It means the same thing as raising each side with a base of 2, and when you do this, the log will cancel out, leaving you with what was inside of it, which is y, equals this 2, we moved it over as the base, and whatever was on the right side of the equation is now the exponent. So again, we get y equals 2 to the x power. Now let's say we have 5 to the x equals y, and we want to write that in logarithmic form. Well, in this case, there's only one way we can approach this, and that is the technical way. There isn't a shortcut method. To get rid of 5 to the x power and to change it to a logarithmic form, we need to take the inverse of each side of the equation. So to take that inverse, the inverse is going to be log of this base, 5. So log base 5. We will plug each side of the equation into log base 5. And when we do this, log base 5 of 5 cancels out, leaving us with just what was in the exponent, which is x, and that's equal to log of y. Log base 5 of y. I should have made that note in both of these. I apologize. So x equals log base 5 of y because we took log base 5 of each side of the equation. There are a few very important notes here that are the most common mistakes when going through these types of problems. First of all, whenever you write a log, if you have more than one term inside of the log, you have to put parentheses around them. For instance, log of 2x does not equal log of the quantity of 2x. Because what's happening in the first one is we're saying we have log of 2, and that's being multiplied by this x. But in the second one, we're saying 2 times x is being plugged into the log. So it's very important whenever you have multiple values inside of your log that you explicitly show which ones are in the log and which ones are not using parentheses. If you don't show the parentheses, then only the very first value is being plugged into the log. The second most common type of mistake is when you have this part here that we took log base 5 of each side of the equation, we did not multiply it. It looks like we're multiplying by log base 5. This is what multiplication has looked like in algebra as far as you've learned algebra to this point. But this is nothing to do with multiplication. Log base 5 is a function. The best way to think about it is like a square root. If I had, for example, x squared equals y, and I wanted to solve for x, I would take the square root of each side of the equation. Would it make sense if I said to multiply each side of the equation by square root? No, that doesn't make any sense, because if you just have a square root symbol floating off in space, we have no idea what to do with it because there's nothing being plugged into it. So this is wrong, just like saying multiply by log is wrong. Always remember, log on its own means nothing. What you plug into the log is what matters, just like a square root. What you plug into the square root is what matters. Okay, so continuing on from there, we say given our logarithmic function of base b, so log base b of x, we can note the domain, range, and graph. So first of all, remember that when you're dealing with inverse functions, an inverse represents a reflection over the line y equals x. And remember what the original graph of an exponential function looks like. It's something along these lines. And it passes through the point 0, 1. So since this is what the exponential function looks like of base b, then if you reflect it over this line y equals x, you'll end up getting this black graph that we have here that passes through the point 1, 0 instead of 0, 1, because again, it is the inverse function. So what is the domain of this function here in black? Well, notice it's getting very, very, very close to the y-axis, but it'll never actually reach it. So we know immediately that in terms of x values, it can never reach 0. and it'll go all the way to the right, which means it goes all the way to positive infinity. And now for the range, it starts all the way at the bottom, which is negative infinity, and then it goes all the way up because of this arrow, so to positive infinity. And this should look somewhat familiar. Remember, the domain of an exponential function is negative infinity to positive infinity, and the range is 0 to positive infinity, like we have here. So, because these are inverses, the domain and range are switched, which is exactly what happened here. The domain of a logarithmic function is the same thing as the range of an exponential, and the range of the logarithmic is the same thing as the domain of the exponential. Okay, now at this point, we'll talk about the two most common logarithmic functions, which are log x and natural log x. While these might not look familiar, these actually are completely connected to the two most common exponential functions we've talked about. Log x is technically just the shorthand form of log base 10 of x. Whenever you have log base 10, you do not write the 10. It is implied that it's there. You just write log x. And likewise, ln x, or natural log of x, is the same thing as log base e of x. But again, we do not write the e. We use this shorthand notation, ln x, because these two are so common. They come up so often that we don't want to always keep writing these bases. It will be an implied base. And then from here we have a couple more facts that are very important. The first one is log base b of b. Take a moment, maybe pause the video, try to think about what this should equal. Log base b of b. Okay, so trying this together, if this were log base b of b to the x, then we know the result would be x. So what is x in this case? If it's not there, then we know the exponent has to be 1. So log base b of b to the 1, the log base b and b will cancel out, leaving us with just 1. So whenever you plug a base into the log of the same base, the result is just going to be equal to 1. Now we have log base b of 1. Take a moment, pause the video. This one's a little trickier, but see if you can't figure out what this should be. Okay, so like I said, this one's a bit trickier. We don't have the base anymore. Log base b of 1, there is no b here, but there is a way that we could rewrite it. Log base b of 1 can be rewritten as log base b of b to what power? Well, b to the 0 power is the same thing as 1. Anything to the 0 power except 0 is equal to 1. And we don't have to worry about b being 0 because logarithmic bases have to be greater than 0. So again, log base b of b will cancel out, leaving us with 0. So if you plug 1 into any log base, no matter what base we have, the result will always be 0. And we can prove that from our graph. Every parent logarithmic function has to pass through the point 1, 0. So when you plug 1 into the log, the y value has to be 0, like we have here. Okay, now we just have 4 examples we need to go through. We'll go ahead and try the first one together, and then I'll have you try the next 3. So, we want to find the domain of f of x equals the natural log of x minus 4. So, for this, remember that the domain of a logarithmic function has to be greater than 0. We can never have a value plugged into it that is less than or equal to 0. So to find the domain of a log, you take what is inside of the log, so in this case x minus 4, and you note that it has to be greater than 0. So solving for x, we'll add 4 to each side, which gives us x has to be greater than, greater than 4. So in interval notation, that would be 4 with a parenthesis because there isn't an equal sign, 4 to infinity. So the domain of this logarithmic function, natural log of x minus 4, is 4 to infinity. It's not 0 to infinity like a parent natural log function's domain would be. Okay, with that in mind, we have g of x equals log of 2x minus 3. I want you to take a moment, pause the video, see if you can't find this domain. Okay, so just like before, we're going to search inside of the log. Immediately we have 2x minus 3, and we know that that has to be greater than 0. So we'll add 3 to each side to get 2x is greater than 3. We'll divide each side by 2, which gives us x is greater than 3/2. So we say the solution is 3/2 to positive infinity, since x has to be greater than 3/2. Continuing on from here, we now want to convert e to the x equals 3 to logarithmic form. So go ahead, take a moment, pause the video. This is like our previous examples. I want you to try to solve this problem, converting this to logarithmic form. Okay, so trying this together, remember if you want to convert exponential equations to logarithmic equations, you have to take the inverse of each side of the equation. What's the inverse of e to the x? It's the natural log. So we take the natural log of each side of the equation. And when we do that, we get natural log and e cancel out to leave us with x equals the natural log of 3. So we just solve for x in our process of converting this to its logarithmic form. Notice I didn't put parentheses around this 3, and that's because there's just one term here. You can always put parentheses inside of your logs, but if it's just one term like 3 or 15 or 5, anything like that, you don't have to put the parentheses. Only if there's multiple values like 5x or 10y do you need them. Okay, so from here, again, take a moment, pause the video, convert the natural log of x equals y to exponential form. Alright, so again, there are 2 ways that we could go about solving this. The first is by raising each side up with a base of e since e to the x is the inverse of the natural log of x, and when you raise each side up with a base of e, the natural log and the e will cancel out, leaving us with x equals e to the y, and this is the exponential form. The other way you could do this, again, is whenever you have a logarithmic equation, remember you can take the base and move it to the other side, and all we have to do is remember that natural log has base e. So we're moving the e to the other side, leaving us with x equals e to the y. Either of these would be perfectly acceptable work to show that you knew how to solve this problem.